Good afternoon, folks, and welcome to the SAYGE Geotechnical Division's second evening lecture for 2024. Just a couple of things to note for the lecture. Teams webinar creates an attendance register at the end of the meeting, hence there's no need to leave your details in the comment section. This lecture is being recorded. If you choose to stay online for the lecture, your consent to the lecture being recorded is implied. For the Q&A portion, please click on the Q&A icon and post your question. I was fortunate enough to chair the organizing committee for the 2023 South African Young Geotechnical Engineers Conference, which was held at Obai Golf Resort in Spa in George in September 2023. Approximately 50 papers were submitted and presented from delegates from consulting firms, construction contractors, academia, mining houses, etc. Professor Eben Rust, our conference godfather, provided valuable feedback to each and every presenter. It was not all work and no play. The social events were well attended and enjoyed by all. What was really astounding was the support we received from industry. Our sponsorship budget for the conference was 200,000 Rand, but in the end, we received nearly 500,000 Rand in sponsorship. We cannot say thank you enough for the valuable support we received from industry. A special mention to our platinum sponsor for the second time in a row, TerraStrata. And last but not least, Yolandi van der Berg from Solar Productions pulled out all the stops and delivered yet another excellent conference. Thank you, Yolandi. As part of the South African Young Geotechnical Engineers Conference, the best paper and the author of the best presenter, and the author of the best paper are sponsored by the SAYGE Geotechnical Division to attend the next International YGE conference. The best paper and best presenter awards recognize not only the quality of the paper, but also the ability to effectively convey complex ideas and findings to a diverse audience. Without further ado, let's get going with the lecture. First up, we have the recipient of the Best Paper Award, Ruan Murison, presenting his paper titled The Compression Behavior of Clays, Clean Sands and Mine Tailings, Frameworks, Experimental Observations and Implications. Ruan, you can take over the screen and do your presentation.
Okay, thanks, Marcin. Can you hear me?
Yes, we can.
Okay, great. I'm sharing my screen now. Is it visible?
Yes, we can see it.
Okay, great. Right, so first and foremost, good evening, everyone. Just like to thank the division for the opportunity to speak to you tonight. It's a real honor and privilege, and it was a real privilege as well to attend the Young Geotechnical Engineers Conference last year and to meet all sorts of new people. My interactions on both a technical and a social front really inspired me for the future, and I'm really excited to get into this community and to walk a journey with them over the next couple of decades or so. So without further ado, I'll get into it. My name is Ruan Murison. I'm a PhD student at the University of Pretoria, and my particular research interest is the hydromechanical behavior of expansive clays. But today we'll be talking about the compression behavior of not only clays, but of clean sands and mine tailings as well. And we'll start off with our idealized frameworks within the realm of critical state soil mechanics, and then we'll move on to some experimental results from the University of Pretoria laboratories, and finally the implications of these frameworks and results. So I want to start off by highlighting the importance of soil state within critical state soil mechanics. And I know that this is a presentation on compression behavior, but I want to start off by looking at soil response in shear. So what I mean when I say soil state, I'm referring to the combination of the volumetric state given by the void ratio and the stress state given here by mean effective stress. So state combinations plotting above the critical state line are referred to as wet of critical. And what that means is if they are sheared, if an element of soil in this state is sheared drained, it will reduce in volume or contract. And if it's sheared undrained, where volume change is not permitted, it'll show a contractive tendency, which means that positive excess pore pressures will be generated. Conversely, states plotting below the critical state line are dry of critical, which means that they'll exhibit volume increase if sheared drained, and negative excess pore pressures will be generated if sheared undrained. Now, how does the state of the soil, in this case, influence response in shear? So I'll start off by looking at an example of a sandy soil, shear drained in triaxial compression. What we have is two samples starting off at the same stress state, one dense and one loose. And then we'll look at a PQ stress path as well as a stress strain curve. And what we can see is for the dense sample, we can mobilize a much higher shear strength than for the loose sample. So we shear it past the critical state line, it yields on the Harslev surface and then softens to critical state. Whereas for the loose case, we don't see any objective peak prior to critical state, but we end up at the same critical state value. And this is probably the reason that if you look at your typical drained limit equilibrium analysis, void ratio doesn't really feature if you're designing on critical state friction angles and you're happy to assume one friction angle for the soil, because the friction that can be mobilized during drain shear is the same for both cases at critical state. Where the real difference comes in is during undrained shearing. And again, we've got two samples starting off at the same stress state. The dense sample might show some volume, or not volume decrease, but tendency for volume decrease, so the generation of positive excess pore pressures initially, after which it will exhibit dilative tendency to critical state. And we can see that we mobilize a much, much higher undrained shear strength for the dense case, than for the loose case, where contractive tendency is exhibited from the beginning of shearing. We mobilize some peak undrained shear strength, and then there's strong strain softening to critical state. And sometimes this critical state undrained shear strength can even be lower than the in situ Q value based on your anisotropic consolidation that might occur in situ. So just a summary on that and why we're particularly concerned about undrained shearing in this day and age. If we have the same sample, loose, starting at the same stress state, one sheared drained and one sheared undrained, we can mobilize a much higher shear strength in the drained case than for the undrained case at both peak and critical state conditions. So where does compression behavior come into all of this? Well, critical state soil mechanics is a concept that marries the compression or consolidation and shear behavior of a soil. We've seen now how the state and stress history of a soil element can significantly influence its response during shearing. How does the element get to that current state? So if you look at a tailings-related example where you deposit an element of soil onto a facility, it's a geologically new material with no stress history, so we know its current state. If we do not at the very least have an opinion on the compression model to which the soil conforms, how would we know what its future state might be and what, as a result, its future response in shearing might be? So I'll say at this stage that I think it's quite curious that we can calibrate entire critical state soil mechanics based constitutive numerical models using only the shear behavior and without ever considering compression behavior, when critical state soil mechanics at its core is a framework that combines compression and shear behavior. So that's just an opinion, I suppose. But if we move on to our idealized frameworks for compression behavior within the realm of critical state soil mechanics, I'd like to start off by just explicitly defining what I mean by normally consolidated throughout this presentation. And what that means is an element of soil, if it is currently at its highest effective stress throughout its stress history, it's considered normally consolidated. That means that a soil element is over-consolidated if and only if it has experienced greater effective stress in its history than its current effective stress. And this is the strict definition which I'll stick to throughout the presentation. Now, we'll start off with an idealized framework for clays. SAYGE, in his original theory of one-dimensional consolidation, assumed that for any given soil, a unique relationship exists between its void ratio and effective stress if it's normally consolidated. So what that implies is a unique normal consolidation line. But SAYGE never actually experimentally explicitly proved this. We have to fast forward a few years in the same lab to Leo Rendulich's work. So what we're looking at here is a photograph of the very first triaxial apparatus. We've got a sample over here, and then we've got the cell, which was actually pressurized using oil or hydraulic fluid rather than water. And interestingly, the deviator stress was applied by simply adding masses to the loading ram. But we're not going to look at the shear behavior, we're looking at consolidation behavior here. And this is just a screenshot from this 1937 paper looking at some of the triaxial consolidation results. So if you trace over these and plot them on a log scale, like we typically do these days, these are your results. So what we're looking at is 4 different samples prepared to different initial void ratios, and then consolidated to various effective stresses with the volume change tracked. And these seem to plot within a very narrow band. Additionally, he prepared 16 more samples, which he consolidated to their effective stress at the beginning of shearing in one step. And those are those X's that we have over here. So there's actually 16 X's plotted here, but they're really plotting on top of each other. What we see here is that all of these results converged into a narrow band, and this was enough evidence for Rengelik to propose that a unique normal consolidation line exists for a given remolded clay. If we fast forward a few years, we get our earliest evidence that we were able to find in the odometer. So what Skempton did here was he prepared 3 different samples, slurry samples that were fully saturated, but at different initial water contents, thus varying the different initial void ratios. And then he compressed these to high stresses and noted that they converged onto a single point at a high stress. It would have been really nice if he had the capacity to load this 1 or 2 steps further so that we could see these following along the same normal consolidation line. This was evidence enough for him to suggest that a unique one-dimensional normal consolidation line exists based on odometer tests. So if we put this all together, we get our idealized compression model for clays within the realm of critical state swell mechanics. And what we have is a unique normal consolidation line, which acts as a state boundary surface. So this separates impossible states from possible states for remolded states of structure, which will become important later. Plastic strains can only be generated upon this normal consolidation line. Then we've got an infinite number of parallel swelling lines upon which strains are elastic. And the initial void ratio of a sample does not influence the position of this normal consolidation line. So for sands, the matter becomes slightly more complicated. What we're looking at here is a constitutive model proposed by Pestana and Whittle for compression behavior of cohesionless soils or sands. And they assume that compression at low stresses is strictly elastic, so all strains are recoverable. And the mechanism driving this, they cited as the rearrangement of particles through sliding and rolling. And then they noted that at high stresses, the compression paths should all converge onto one unique line called the limiting compression curve. And it's very important that they noted that the mechanism that drives this LCC response is particle crushing, which is a collective term they used for any breakage or fragmentations of particles. So really important, limiting compression curve behavior only occurs if particle crushing is noted. And this is applicable to high stresses. If we look at any of the experimental results from other authors that they presented to verify their constitutive model, convergence onto the LCC only occurs at very high stresses, often over 10 megapascals. One limitation, though, is that they assumed that the compression behavior at low stresses is elastic, and that seems counterintuitive. If you have a loose packing of sand, you were to load it and allow the particles to rearrange themselves, and then you remove the load, it's unlikely that it would rebound back to the same initial volume. So along come Jeffries and Bean in 2000 and present what is probably the most complete experimental program proving the compression behavior of sands that we have access to. They tested an oak sack sand, which is a clean sand with a D50 of 330 microns and a fines content of 0.7%. And importantly, all the tests that they considered were normally consolidated from the outset. Now, we see quite a wide range of void ratios. So how have they achieved that? Well, the moist temp samples, it was quite easy to create loose samples in the state that was stable. And then to create denser samples, all they did was they took dry sand and vibrated it a little bit, which allowed rearrangement of the particles without imposing any stress history on the sample. So without any external stress, the sample is still at the highest effective stress it's ever experienced in its history, and thus is, strictly speaking, normally consolidated. They then loaded all of these samples, and they noted that the compression paths, which are normal consolidation lines, given that we have initially normally consolidated conditions, these compression paths were approximately parallel. Another thing that they did was they determined the critical state line for the sand, and then used the original CamClay model to plot what they called a pseudo-normal consolidation line. So that is the state boundary surface predicted by the original CAM clay model, and it's simply parallel to the critical state line and offset by Euler's number. And they then noted that 3 of their samples happily lived above the pseudo-normal consolidation line, which means that the CAM clay model could not predict the state boundary surface for the sand. Then what I'd like to do is zoom into these 4 tests that I've highlighted in red. And each of these tests was loaded and unloaded, sometimes a number of times. And what we see for each of them is this classical form of a normal consolidation line and a swelling line, which is flatter than the normal consolidation line, meaning that since we don't recover all of the strains imposed during consolidation, plastic strains must have occurred. So we see elastoplastic behavior here rather than strictly elastic behavior. So if we call this a normal consolidation line and then the green line a swelling line, we see the same form for all of the tests where we've got this backbone normal consolidation line and a number of parallel swelling lines. If we put all of this together, we get our idealized compression model for sands, which has an infinite number of parallel normal consolidation lines, upon any of these, there can be plastic strains that are generated. None of them act as a state boundary surface until they converge onto the limiting compression curve, which here is considered to be state boundary surface. The initial void ratio does influence the position of the normal consolidation line. And then again, we have an infinite number of parallel swelling lines, as we did with clay. So yes, just a summary with the 2 idealized models next to each other. And if we extend this to include the critical state line, this is what it looks like. So for clays, the assumption is that the normal consolidation line and critical state line are parallel, regardless of the stress level. So for our practical stresses, the NCL and CSL would be parallel for clays. That's not true for clean sands, where the normal consolidation lines are not parallel to the critical state line. It may be fair to assume that the LCC and the CSL would be parallel, but that's only applicable to high stresses. And the reason that that's important is for clay, if it is normally consolidated, it is always in a wet-of critical or contractive state, regardless of the stress state. Whereas for clean sand, we could happily be normally consolidated and still dry of critical or dilative if we're traversing along this line, for example. But if we were to load this far enough and eventually cross over the critical state line, we move into a wet-of critical or contractive regime. So that's enough on all the theory for now. Let's look at some real experimental data from our laboratory at the University of Pretoria. So I'll start off with expansive clays, which, as I stated, is my particular field of interest. So this is the section of the presentation that's actually relevant to the scope of my PhD. And we've got 2 sites in South Africa from which we've obtained highly expansive clay samples. One is close to Vredefort, which is called the olive clay, and one close to Steelpoort, which we've called the black clay. And I've plotted the location of these 2 sites on top of the distribution of expansive clays in South Africa, plotted by Williams et al. In their state-of-the-art paper in 1985. And we can see that the olive clay is in a region where severe movement of foundations due to heaving of expansive clays is commonly reported. And the black clay is in a region where some severe movement has been recorded in the past. But a background on these 2 clays here, we've just got photographs of compacted samples of each of the clays. The black clay is marginally finer than the olive clay, but both of them have high clay content in excess of 50%. The olive clay is more plastic than the black clay, but again, we have high PIs for both 82 and 55, so really plastic stuff, really expansive stuff. And finally, I'd like to highlight from our X-ray diffraction results, the predominant mineral constituent of both clays is smectite, which is the mineral group to which montmorillonite belongs, and that's the clay mineral that often drives expansive behavior of soils. So let's look at some odometer test results. What we're looking at here are swell under load tests, followed by consolidation. So a number of tests or a number of samples are built at a void ratio corresponding with the in situ void ratio. Then each sample is loaded to a particular stress, and then the cell is flooded, allowing swell to occur. So that in situ void ratio is approximately 0.85 for the olive clay and approximately 1 for the black clay. And if we look at the 1 kPa test, for example, here we started at a void ratio of 0.85 and allowed the sample to swell, and it swelled 43%. So it really is very expansive stuff. Then after bringing the sample to a state of 0 suction, it's conventionally consolidated. And if we look at the compression parts of each of these tests, at high stresses, they converge into this narrow band, which indicates a unique normal consolidation line. It is important to note that this only occurred at high stresses for this state of structure. So if we were to stop the tests at 400 kPa, for example, we really wouldn't know much about this clay, but the magic happens at high stresses. And then we have what seem to be parallel swelling lines as well for practical purposes. The case for the black clay wasn't as simple. So if we look at the 1 kPa, 12.5 kPa, and 50 kPa tests, these all converged into one band of normal consolidation lines, whereas the 100, 300, and 800 kPa tests converged into onto a different normal consolidation line that plotted above the previous one. And the reason that we've given for this is destructuring that might have been imposed upon the sample during swelling. So theory is that some strain energy is built into the structure of soils, and if yielding of the structure occurs during either compression or swell, the strain energy is released, which causes a softer response, which we noted for these three samples. We can look at this in a little bit more detail by plotting the compression and expansion indices, so the slopes of the normal consolidation line and the swelling lines, against the volumetric strain imposed upon the sample during soaking. And we see that even though strains in excess of 40% were experienced by the olive clay samples, this didn't bear much influence on the compression index at all. Whereas for the black clay, any samples that were swelled more than 5% experienced a softer response, and there's this distinct jump over here. So structure is clearly important, and I'd like to highlight a couple of things about how structure influences the compression and response of soil as well. But first, I'm going to look at why we think that these two clays might have behaved differently. And the reason that we've come up with is the microstructural arrangement of the two clays. So Jensen Alonso proposed these two microstructural arrangements that are typical for expansive clays in their extended Barcelona basic model for expansive soils. What we have here is these elementary particle arrangements, which are literally just stacks of a few clay platelets. And these are arranged into a continuous matrix for microfabric type A. Microfabric type B is actually a structure that was also proposed by Ian Brackley of the CSIR in South Africa in the 1970s. And Jensen Alonso noted his influence in developing this microstructural arrangement. So what happens here is that your elementary particles organize themselves into aggregations or packets. And thus you've got pores between the elementary particles within the aggregations, and you've got pores between the aggregations as well. So usually this can be identified by a bimodal pore size distribution. So then what we've got is scanning electron microscope photos of both the black clay and the olive clay. And it seems that the black clay is organized into this continuous matrix or microfabric type A, whereas the elementary particles have organized themselves into packets or aggregations for the olive clay. We then suggested that microfabric type B might be a more robust microfabric since larger swelling strains were experienced by this clay without destructuring the soil. So if we move on to a generalized framework of how soil structure might impact compression behavior proposed by Leroyal and Vaughan in 1990, here we've got our idealized framework that we looked at earlier, where the intrinsic normal consolidation line separates impossible and possible stress states. And what I mean by intrinsic is it's a property that is not influenced by structure or stress history. So this is recorded by preparing a sample where you've erased any effects of structure and stress history, so by reconstituting the sample. Structured soil might behave slightly differently. So if you were to initially load the sample, it would respond in a flatter manner or stiffer manner. And if yield were to occur, yielding of the structure, this could occur, by the way, in compression or in swell, which we saw earlier. And if yield occurs, further compression would cause further destructuring, and we would eventually tend towards the intrinsic compression line. So if we combine these two plots, what we have is a structured soil venturing into space that would otherwise be impossible, and thus the term structure permitted space follows. So states that are only attainable due to the presence of structure in soils. And here we see that during further destructuring, we tend towards the intrinsic compression line. So if we look back at these results, these broken lines represent the intrinsic compression index and expansion index for soil. And we see that our compacted samples exhibited a much stiffer response than our reconstituted sample, which indicates this presence of structure. Whereas for the black clay, our compression index for the destructured samples or partially destructured samples is tending towards the intrinsic compression index. So if we were to load these any further than we did and allow the structural bonds to continue to break, we would likely approach this line. So next up, I'd like to move on to results for silica sand. So this next section is actually the scope of the original YPE paper, which was titled The Influence of Sample Aspect Ratio on the One-Dimensional Compression Behavior of a Silica Sand. So we start off by looking at the boundary conditions for a fixed ring odometer sample. We know that compression and drainage only occur in one dimension, which is vertical, and we've got a full lateral restraint, so we can call this K0 consolidation. The pore pressures and lateral stresses in conventional odometer are unknown, but we know that at the end of a consolidation phase, excess pore pressures are zero and pore pressure within the sample itself, for all intents and purposes, would be zero as well. If we make that assumption and we also assume that the sample self-weight is negligible for the small sample, these are the free body diagrams that apply to a fixed ring odometer sample. And what we see here is that we have an applied stress to the top of the sample not being equal to the stress recorded at the bottom if any shear stresses are mobilized at the interface between the odometer ring and the soil. And a difference in top and bottom vertical stress would result in a conformance error. We'd be under measuring the compression because not all of the effective stress is being transferred to the bottom of the sample. So given these assumptions and free body diagrams, we can actually determine an expression for the difference between this top and bottom stress. And we see that it's a function of the average shear stress mobilized along this interface and the H/D ratio, the aspect ratio of the odometer sample. So there are two things that we can do to minimize our error. The first thing is simply to polish the ring as best we can to reduce this angle delta and reduce the shear stress that we're able to mobilize on the interface. And the second thing is to choose a sample size that has a larger diameter relative to the height of the sample and minimize this aspect ratio. So for this reason, the ASTM standard specifies that H/D ratios of less than 40% must be used. So the diameter of the sample has to be at least 2.5 times greater than the height of the sample. And the question I wanted to ask in this paper was, is that a sufficient assumption for dense granular materials where large sidewall frictions could be mobilized? If we look here at our 50 millimeter diameter, 20 millimeter high odometer ring, the photo doesn't really do it justice, but it feels quite ridiculous to test something like this when you've applied a large force in order to get the sand into the sample. And looking at it, it just feels as if the boundary conditions have to limit the compressibility that you can measure. But it complies with the standard, so I wanted to test whether that is a fair assumption. So the material that was tested is a fine uniform silica sand that we usually use for centrifuge modeling at the University of Pretoria. It's got a D50 of just under 100 microns and a fines content of just over 20%. And the critical state friction angle is 33 degrees. So it's not quite a clean sand like the one that Jeffries and Bean looked at, but it's still a uniformly graded sand. The testing program was to use these three different odometer rings that we have access to in the laboratory, and thus three different aspect ratios to test two different density conditions. So 3 loose samples were prepared and 3 medium dense samples were prepared. These were carefully moist stamped at a void ratio, a water content of 8% to a carefully controlled void ratio. And the reason that I had to be so specific with this is that we know that the initial void ratio influences the compression behavior of a sand. So if you're trying to compare apples with apples across 3 different samples, you need to get to as identical as practically possible an initial condition. So all of the testing was conducted in our new GDS automatic odometer. Seating stress of 5 kPa was applied to the sample unsaturated, and then the cell was flooded to saturate the sample. After saturation, sample was incrementally loaded to 1.5 MPa and then incrementally unloaded back to its 5 kPa. Primary settlement and swell for all phases in this testing program only took a few seconds because we have a highly permeable sand, but the increments were still left for 30 minutes to ensure that all excess pore pressures had dissipated. So let's look at some of the results. The loose samples were considered to be initially normally consolidated for two reasons. Very little compactive effort was required to form the samples, so there was no significant stress history applied to them. And each of them also collapsed by 2 to 3% upon saturation, meaning that they were initially in a metastable state that was only attainable due to suctions in the sample. So we see that collapse over here. The medium dense samples were initially over-consolidated because they required some compactive efforts. They could be compacted by hand, but some stress history would have been imposed. And Casa Grande constructions were done on each of these to determine the pre-consolidation pressure or the yield stress. And so beyond 120 kPa, we could consider these to be normally consolidated as well. So looking at the three loose samples with our different H/D ratios, they start off at a similar void ratio, and then for all practical purposes, we're looking at the same compression curve and same unloading curve here. So there was an insignificant influence of sample aspect ratio on the compressibility behavior of our loose soil. Looking at our medium dense sand, once we've moved into the normally consolidated regime, we're looking at three very different compression curves. So as we increased our aspect ratio or decreased our diameter relative to the height, the compressibility decreased, which means that we're under measuring compression because of our boundary effects. So if we plot all of these on the same set of axes, we see that the 75 millimeter medium dense sample seems to have a normal consolidation line that's approximately parallel to that of the three loose samples. And we can see that here as well if we compare the compression index to the compression indices of the three loose samples. So that then seems to conform with the framework that we developed earlier. The expansion index for neither set of tests, or for both sets of tests, the expansion index was not significantly influenced by sample aspect ratio. So why are we seeing what we're seeing? Well, if we start off with the medium dense samples in a dry of critical state, any shear stress mobilized along the soil ring interface would result in dilation. And that's a mechanism which is driving volume increase and counteracting our compressive mechanism through the increase of effective stress. So because of these counteracting mechanisms, we should witness reduced compressibility. The reason this is a bigger issue for smaller samples is if we've got the same shear stress being mobilized at the interface and the same zone of influence of this dilation, the smaller our plan area gets, the bigger the proportion which our dilation zone takes up of the sample, and thus we have bigger error. Another way to look at this is the horizontal stresses in the medium dense samples are greater than that of the loose samples, resulting in a higher mobilized shear stress. So per the equation that we developed earlier, it's likely that the error would be bigger for denser soils in the first place. So what do we recommend looking at all of this? If you're specifying a testing program for pedometer tests on a granular material, you want to use as low an H/D ratio as possible. So use the biggest diameter that the lab has available. So in summary, we've got our sand results here where we've only considered the medium dense test where H/D was sufficiently minimized, and then we look at our three loose tests. And here we have parallel normal consolidation lines. So it behaves like the idealized framework for clean sands. And as discussed as well, we've got results on a clay which conform to the idealized framework for clays. So you might be asking then, what about mine tailings? So in the first place, if you have a non-textbook soil, something that's not a clay or a sand, it is a good idea to design a testing program to test whether it conforms to a clay-like or a sand-like compression framework. There have been a few studies published on tailings, different types of tailings, and they've shown conflicting results. Some behave like clays and some behave like sand. So it's really important to test this. And why might the behavior of a tailings be different? Well, we can look at the different factors that can influence the compression behavior of a soil. starting off with particle shape and the grading as well. So this influences how the particles are able to rearrange themselves when compressed, and also what the possible packing arrangements and thus possible void ratios are. The second thing is the mineralogy of the soil. So are there any clay minerals present? And as a rule of thumb, clays behave like clays, not just because of the presence of clay size particles, because of the presence of clay minerals and how these minerals interact with water. The second thing to look at, perhaps more applicable to granular soils, is the strength of the grain minerals that make up the sand. So your tensile strength would influence at what stress a particle could split, and the compressive strength would influence what stress it would be able to crush. So a quartz sand, for example, would traverse onto the limiting compression curve due to particle crushing at a much higher stress than something like a carbonate sand, which has softer grain minerals. And the final thing is structure, which is the combination of fabric and cementation. So we've looked at this in a little bit of detail already. And for the sand tests that we've just looked at, as well as the tailings tests we're about to look at, the fabric was kept consistent through moist tamping, and all of the samples were remolded to remove any influence of cementation. So structure thus shouldn't really be a factor in the case that we're looking at. So let's look at this case study of the gold tailings that we have available in our lab. So a little bit of background. The mine is on the east rand of Johannesburg. The ore is mined from the Witwatersrand supergroup. It's an upstream constructed facility utilizing spigot deposition, and our samples were all taken from the outer wall, so from the structural zone of this upstream facility. So it's the coarser fraction of tailings within the facility. That doesn't necessarily mean we're looking at, by definition, a coarse tailings, but it is the coarser fraction on the dam. So this is a photograph from Yashay Narayan-Sami's PhD of what the structural zone actually looks like. So as we know with tailings, it's often highly layered. We've got these coarse layers and the fine layers that appear wetter. So it is quite layered and thus quite variable inherently. But the approach that we take to testing tailings at the University of Pretoria is to test an average grading. So to blend all of this, have all of these different layers in one sample with a uniform is the wrong word, a consistent grading. And that's what this looks like. Then what we have here is an example of tailings that was slurry deposited in a bucket and then sampled using a tube sampler. So here we see in the sample, we don't have the layering that's apparent in situ, but we rather have one sort of average grading. I'd just like to note we did trim the top of the sample before we tried to test anything here. So what we're going to look at is results from a case study that we published in the Geotechnical Testing Journal, trying to investigate whether the normal consolidation line for this gold tailings was unique. What the average grading looks like is something that classifies as a non-plastic sandy silt. It's got a D50 of 63 microns, so it is quite fine. It's got a fines content of 50%. And the critical state friction angle is 35 degrees, which is quite high and like a typical sandy material. And I'll note as well from the 30-odd tests that Yashay has conducted throughout his PhD, the shear behavior of the soil is not something that you wouldn't expect for sand-like material. So we seem to see behavior similar to that I presented at the beginning of this presentation for the shear behavior. But let's look specifically at the consolidation behavior first. So before even looking at the results, would we expect sand-like or clay-like behavior just by looking at this tailings? So here I've got a scanning electron microscope photo of the tailings, and I've indicated for scale the silt sand or the coarse fine particle size boundary. So here we're looking at both fine particles and coarse particles, and all of them seem to have a similar shape. We don't have fines that have a sort of platy shape. All of these are angular. So at first glance, it doesn't look like we have any clay mineralogy here. And that was confirmed by the XRD results, where this is 96% quartz. So for all intents and purposes, nearly identical in terms of mineralogy to the silica sand, which we just tested. So we took some EDS photographs of the sample as well to see the elemental composition. So this is energy dispersive spectroscopy. And how it works is we can map out qualitatively the elements present within the sample based on the X-rays which are emitted from the sample. So if we look here, we've got our coarse and our fine particles all containing silicon and oxygen in the same space, so SiO2 or quartz. So it's not as if only our coarser particles are silica. Silica seems to be everywhere in this case, which makes sense because it's 96% silica in any case. We've got some aluminium as well, and the reason for this is that aluminium oxide is a compound that is part of both the pyrophyllite and the muscovite, which we identified in the XRD results. And then we've got some iron in the sample as well, which is a part of the pyrite. So in terms of mineralogy, in terms of particle shape, this is very close to the silica sand we just looked at. The one big difference is in the grading. So first things first, it is finer, but if you were to see a uniformly graded silt, for example, you wouldn't expect that to behave differently if the particle shape and mineralogy is the same. It wouldn't behave differently to the silica sand then. The big difference is in the shape of the grading curve. So it's more well graded, which means that the particle arrangements that can be attained might be different and the compressibility might thus be different. But is this enough to drive some compression behavior that's not sand-like and have it change to something else? Well, we'll see. So all of our samples, again, were moist stamped at a water content of 15%. Odometer rings of at least 75 millimeter in diameter were used. So based off the fact that this critical state friction angle is quite similar to the silica sand, this should be sufficient to minimize any errors due to the mobilization of sidewall friction. Then samples were moist tamped to initial void ratios ranging between 1.2 and 0.6. Again, a seating stress of 5 kPa was applied, the cell was flooded, and any potential collapse was observed. Then all of the samples were incrementally loaded to high stresses up to 3.2 MPa. And again, primary compression or swell generally occurred within the first few minutes of compression and unloading, but each increment was still left for 2 hours to ensure that all excess pore pressures are dissipated. Then some additional tests were done, which were initially compacted to a void ratio of 1 and only loaded to smaller stresses. And after all of these tests, we sent each of them for a grading analysis to determine whether any particle crushing had occurred, and if so, at what stress does it start to occur? So let's look at some of the results. The void ratio between 1 and 1.2 was considered initially normally consolidated, again because these samples had little to no compactive effort required in order to form them, and they exhibited initial collapse, as we see over here, meaning that they were in an initially metastable state. Samples at a void ratio of approximately 0.8 were overconsolidated. They required some moderate compactive effort that could be done by hand, but it required a tamper and a hammer. And finally, our sample void ratio of about 0.6 was definitely heavily overconsolidated. We needed a hydraulic press to form the sample, and we compressed it with 2.6 tons of force, or 5.7 MPa. So definitely overconsolidated with a big stress history initially. And with all these results, they seem to converge into a narrow, normally consolidated line band. All of the swelling lines also seem to be parallel, so our unloading lines and our initial loading lines for the overconsolidated samples are also parallel for practical purposes. If we look at this in a bit more detail, we've got our expansion index during unloading and during the initial loading of our overconsolidated samples. These numbers are quite similar. And then the compression index of our samples other than the 0.6 sample were all very similar as well. Now, this doesn't prove that anything is unique. All it says is that the normal consolidation lines are in fact parallel. We need another tool to prove that they are occupying the same space, which would imply a unique normal consolidation line. What we used for this is this M value proposed by a research group headed up by Professor Coop in London. And what they recommended was comparing the specific volume or the void ratio at a high reference stress to the initial specific volume. What that means is if you plot these out and you get an M value of 0, the initial specific volume had no influence on the end specific volume, meaning that you've got a unique normal consolidation line, or perfectly unique normal consolidation line. For an M value of 1, a one-to-one relationship between these two mean that all of the compression paths were parallel throughout loading, and the initial specific volume significantly influences the end specific volume, and this is sand-like behavior. So from this research group specifically, they have a few studies. The first recorded an M value of, I think, 0.14, and they considered this to be evidence of a unique normal consolidation line. An M value of around 0.4 was said to be uncertain or inconclusive, whether it was clay-like or sand-like behavior, and an M value of close to 0.7, they said was evidence of sand-like behavior, parallel normal consolidation lines. So given all of that and our low M value of 0.2, it's probably fair to say that the behavior we're looking at here complies better with clay-like behavior with the unique normal consolidation line and sand-like behavior that we saw. What you might say is, how do you know that you've not traversed onto the limiting compression curve, and that's why you're occupying the same space for each of these compression parts? Well, as I said, we did gradings before and after each test. So the markers that we have here are the average initial grading, and then we've plotted the maximum stress which any sample had experienced versus grading curve. And what we see here might be some evidence of a marginal increase in fines content if we look at the 2.4 MPa sample, then the 3.2 and the 1.6. But then we go and look at the 100 and 400 kPa samples, and somehow the fines content has reduced, and that's certainly not possible if you have a unique initial grading. And luckily, Yashay has done a whole bunch of tests where 32 different grading samples were taken throughout the course of his PhD, and the grading curve plotted within this envelope over here. So there is some inherent variability in the gold tailings. And only one of the samples that we took over here plotted outside of the envelope created by the other 32, meaning that any particle crushing, however marginal, that we could have seen was masked by the inherent variability of the gradings of the tailings. So we cannot provide any significant evidence of particle crushing, and under stresses of 3.2 MPa, given what we saw earlier for quartz sands, it is unlikely that we had converged onto a limiting compression curve. So if we put all of this together, the compression behavior of this tailing seems to comply best with the framework for clays. Completely run out of time to be able to discuss the triaxial testing in any detail, but as part of the study, some triaxial consolidation tests were order to establish the isotropic normal consolidation line, which, if we assumed a constant K0 value for our odometer tests, was approximately parallel to the isotropic line, which complies well with the theory as well. And then drained and undrained shearing tests in triaxial compression were used to establish this critical state line. And there's, in addition to these, like I said, 30-odd triaxial tests in Yashay's PhD. So definitely keep an eye out for that. Some very interesting stuff. But if we were to summarize all of this, our normal consolidation line and critical state line that we determined were approximately parallel as well. So the slopes of these two lines are not identical, but over any sort of practical stress range between 50 and 400 kPa, the slopes are similar enough and the lines get nowhere close to crossing each other. So for all practical purposes, this is behaving, again, more like a clay than like a sand in terms of its compression behavior. So what would all this imply for a tailings material? Well, as we said earlier, if the compression model to which your tailings conforms is clay-like, regardless of the stress level, if you are normally consolidated, you will always be wet of critical or contractive. So I'd like to just emphasize this is a very specific case to our facility, our material, our element tests. It's definitely not universally true for tailings, and this would depend on the tailings material you're considering. But if this were to be the case, what it means is if an element of tailings in your structural zone is below the water table, for you to assume that it's dry of critical, you need to have great confidence in any mechanism that you believe is causing significant overconsolidation of the material. Of course, we have the theory that densification during desiccation causes overconsolidation of tailings. And this is one mechanism that you could look at. But as I say over here, you need to have great confidence in that mechanism if you want to believe that tailings below the water table that's become saturated again is still overconsolidated or dry of critical, if this is the compression framework to which your tailings complies. So that brings me essentially to the end of my presentation. So some things that I'd really like to note. It is our opinion that an understanding of the compression behavior of soils is as important as an understanding of the shear behavior for considering both the volume change behavior as well as a potential response during shearing. And there are some consequences that follow given the assumption of the compression framework to which your soil might comply when looking at shearing from a normally consolidated state. And if we look at some more specific conclusions for the different soils, it is advised to minimize the H/D ratio when testing a granular material as far as practically possible. So specify the largest sample diameter that you can for your lab testing program. And then for the expansive clay, soil structure is an important factor to consider because it influences the slope and the intercept of your normal consolidation line. Finally, for the gold tailings that we considered, with fines content of 50%, this complied with a compression framework for clays. And what it means is that this tailings would always be wet of critical if it is normally consolidated. So finally, I'd like to say thank you again for the opportunity to present today. I'd like to invite anyone that has any questions, comments, criticisms to send me an email at any stage. I'd love to engage with the community as much as possible. And I'd like to say a thank you to our team from the University of Pretoria that made the YGE special. We've got our 3 undergrads that came with, Ross, Lizzie, and JP. And then, of course, our postgrads, Yeshe, whose work over the last few years and his guidance have been really important to my development. And then, of course, Opeyemi as well, who happened to fly out to Kenya for another conference the day after YGE, but he flew back to join us for our road trip again. And as I show here, he never really left us in spirit. So thank you very much again. I really appreciate the opportunity. And from my side, congratulations to Duan for winning Best Presenter at YGE. I really, really enjoyed your presentation back then. So I'm excited to see what you have for us today. Thank you.
Thank you, Ruan, for a very interesting presentation. You've gone a bit over time, so I'm going to have to skip the Q&A. We'll see at the end if there's a couple of questions for you. So Duan, we'll jump right into your presentation. So Duan, the Best Presenter Award was awarded to Duan Swart. He'll be presenting his paper titled Between Rock and Soil, Weathering Products from the Decomposition of Dullstroom Formation and Manganese-Rich Dolomite.
Thanks, Masain, for that intro. Yeah, everyone, good presentation. It's a bit higher grade for me as a geologist, but yeah, I really enjoyed it. Can you hear me fine, Masain? Just want to make sure.
All good, yes.
Okay, cool. Before I begin, since I'm here because I did a presentation at the beginning of the year, I'd like to tell you a story about the presentations I've done over the past years to various different audience, from soil physicists to agriculturalists, soil scientists, today to geotechnical engineers. But one of the extremes was for a STEM club at a local primary school where I live. And how do you relate? Well, every presentation needs a wow moment. And how do you find this wow moment to relate geology to a grade 7? And I thought, everyone knows about toothpaste, and in your toothpaste is fluorite, which is a mineral that we have to mine. And I was trying to explain to these grade 7s, why we use it. There's a thing called Mohs hardness scale here on the right. And, your teeth sit at kind of just above 4, fluorite sits at 4. So it's in your toothpaste because they grind each other away and it cleans your teeth. Whereas cheaper toothpaste use quartz. It's a lot cheaper to mine, and but it destroys your teeth over time. So I was showing them how the fluoride that can't scratch glass and quartz can, and I was they're all excited to get these samples in their hands. And then as soon as I started handing out the samples, I could see they grab the fluoride first and they look at it, and if you look at that image, it looks like if toothpaste had to be a rock, it would be this one. And they all picked up the sample and straight away smelt it, and were disappointed that it didn't smell like toothpaste. So, you try to find a wow moment, but sometimes it's a wow moment that you didn't realize that they have. But their wow moment was that it didn't smell like toothpaste. But hopefully I can get a wow moment to you guys tonight. So just to give you a brief overview of what I'm going to present, it's just 2 case studies, looking at the weathering profiles for the Dullstroom lavas and also dolomite residuum. And I'll be covering kind of the structure and chemistry of these 2. The point of the study from a zoomed out position is that we're trying to understand how a completely weathered, extremely weak rock, so that's less than 1 MPa, behaves, and how that's governed by the soil structure and chemical composition. And then the kind of thing we want to answer here is, where is that transition from soil behavior and rock mechanics, both from a mechanical and a fluids point of view? Why are we looking at this in South Africa, just from the water research side, is 97% of our fresh water sits in the groundwater, and most of these diagrams showing water cycles, they kind of ignore the small area called the unsaturated zone, the beta zone, and this is where our geological material usually sits. It's kind of they focus on the stuff having above surface and then also in the phreatic zone. So we're looking at this unsaturated zone. The area or the concept I want to get across is a weathering profile. So we're not looking at horizons, we're looking at the change of behavior over a profile. So the image of the right is a photo of the profile from a burrow pit at the Dullstroom site. The completely weathered rock at the bottom. What defines a completely weathered rock is that the rock has weathered to the point where it still has its original rock structure and texture, but most of the primary rock minerals have transformed into clay minerals such as kaolinite or iron oxides. And then a concept that I just want you to remember throughout this presentation is that for the rock structure to remain, the volume has to remain the same. So even though the material is being removed, the volume is staying the same. And then if you get to a more weathering point, you'll get a residual soil, and that line is defined by when the rock structure is lost, and it kind of typically on this kind of rock becomes a reddish clay. So that's your residual material. If I can explain it to you on a diagram, you start with a rock somewhere. There's a weathering front near the surface and near the joints. That's where the most weathering occurs. It rains. There's a slightly acidic rain falls on the rock before it goes to the joints, and then as it flows to the joints, it removes kind of your typical rock ions from crystal structures, and then this either gets leached away or taken up by plants. And over time, the weathering front will move down deep into the surface, and then you'll have this increase in the state of weathering alteration as you move up to the surface. Why do we have to look at the porosity or the rock structure? Why is it interesting? It's because it'll govern your porosity, and the rock structure the completely weathered relic structure is dependent on your parent rock, how it formed, its stress history, and the resultant kind of infill that you get. So images here are just various different rocks. There's tillite here, just to show you how different it can look. Joburg granite, bushveld granite up top right, and then this is from the Dullstroom site. And then also the idea I'm trying to get across is that even though this material excavates as a soil and sometimes even logged as a soil, it's less than 1 MPa, but it'll still have its rock structure. So typically the stuff's influenced by the structure and not texture, that once it's excavated, you take it for an F5, it won't be influenced by that. Why is porosity important? It's where the magic happens. Anything in geotechnics or geology, the water with unsaturated soil mechanics, it all happens in the pores. It doesn't happen in the grain. Yeah, that's why doing the grading analysis always isn't the best thing. That's why you need undisturbs, which we do, which is fine. Just to give you some context, you get 3 different types of porosities. Primary porosity typically in your soils, secondary in your rocks, and then your tertiary is kind of what you get in your dolomites. So just start on the case study now for the Dullstroom site. We did other tests, but what I'm going to cover today is just the tube sampling that we did. That's just a photo of me from a different site, trying to tap into those PVC tubes. These are kind of the results I'll be showing for this case study. The sample size is about as big as that tube there. And what we did was where we got the tubes in kind of close to that completely weathered, highly weathered boundary, 2 in the kind of in the middle of the completely weathered, and then 1 in the residual profile or residual horizon. What we did with those tube samples, we sent it for X-ray computed tomography. So it's essentially a CT scan that you can do at the hospital, that you do for your brain sometimes. How that works is on the left here, you put the sample into the machine, or if you've gone for a CT scan, you get kind of shuffled into a machine, and then X-rays come flying at you at a certain voltage, and then they hit minerals or samples. In this case, I just put kaolinite, hematite, and then air that's in your pore for reference. And how this works is the amount of X-rays that get absorbed is related to the atomic number of the elements in the mineral, and then which then relates to the density of the mineral as a whole. So the more dense your material is, the more X-rays it absorbs, the less passes through. So air would be kind of all the X-rays that you shot through it would kind of go through it. And then there's a detector on the other side of the sample, which then picks up the X-rays coming through. And through softwaring and slice creation and things, you get a slice, and that's kind of what you see, what the doctor shows you, where your bones are kind of white, and your kind of blood, your muscles, and you know, I wouldn't want to say a hole, but like, you know, air pockets in your body are kind of black. So all the images I'll be showing now is of the slice. So your more dense stuff is white, your less dense stuff is black. So these are kind of the 4 tube samples that I got. The deepest one's here on the right, and then there's an increase in state of weathering alteration. So essentially this is moving up the profile from right to left. This is now after I've done the CT scan. I cut them open and took photos of it. I think I want to highlight here is the benefit of a CT scan is that it can be done at any moisture content, and there's no sample preparation. So as soon as you push the tube in, you can get your sample out. It's fairly easy to do. You close it up at the ends, send it, put it in a box, send it to the lab. They scan it. They can send it back to you for more testing if you want to do densities and stuff like that. So you get the best picture of the soil structure and the mineral relations, because there's no fiddling around with trying to cut it into a certain shape or trying to dry it out or something like that. And what I found, what we can do with it, you can identify and analyze pores. The size of the pores that you can analyze depending on the sample size. So bigger the sample, the bigger your pores. The bigger the view, the bigger the sample, the bigger the view. That means your pores that you can pick up become bigger. So the smaller the sample, the smaller the pores you can pick up. So you can go to, I think, 2 nanometers if you have a very small sample. But in this case, we're looking at kind of a bigger sample. So we want to look at the macro structure. So we kind of only got to like 0.1 of a millimeter for the pores. And then you can also relate the structure of the sample and also material density, since the X-ray CT scan is based on densities. So this is now the least weathered sample. So this is the one all at the bottom. This is a slice, just to kind of show you what you can get from it. So the little legend of the arrows here on the right. This is the same sample with a top view and a side view. This blue line shows the cross-section plane of the top view. So you can kind of nicely see the structure running through. You can see some mineral grains, you know, lighter means more dense. So this is most likely a microcline, and everything around is probably kaolinite, which are secondary minerals. Same sample, but looking at using a density scan. So you can cut off a certain degree of a window of density to kind of only focus on the more dense material or the less dense material. So for this, I focused on the more dense material because I'm trying to see what's running in the structures. So here's the structure running on the left. The kind of the very dense material follows the structure, and then this is the above it and below. It's kind of a scatter that I'm not focusing on or orientating the sample in a way. But all these kind of denser materials that you pick up here follow a structure for the sample. If you go a step up into the completely weathered rock, it's moderately weathered. You can see on the slice on the left, the rock grains are kind of lost. You see a lot more black little pockets or black holes. Your structure isn't as pronounced, but you can still see that the more dense material kind of still follows the structure, but it's the degree of which it's more dense is higher by it being a bit more red compared to the previous slide. And then now this is the most weathered sample. So this is the residual soil. So you can see that the structure is kind of completely lost. A lot more black holes, telling me that there's a lot less dense, and the denser material is much more variable in this sample. The other thing you can do, so this is a video of the 3D porosity analysis. So once you have all your slices and all your you can from all the angles, you can then put this through a software called volume graphics, and then you can generate these. I'll just play that again for you. You can generate these 3D pore analyses, and what you can see from this, I'll show you in the next slide, that there is some sort of a pore orientation going on here. So this is the sample that you saw in the video, just from kind of the right, the front. You can see that we didn't get very small pores. It's only 0.16 on this sample. But what I want to show you is that the pores do have a preferred orientation, which is parallel to the structure that we saw in the logs and then also on the density scans. In this sample, just for interest's sake, we picked up 4,027 separate pore spaces, and there will be a lot more in a lot smaller pores. And just to show you, compare it, this is the most weathered sample on the right, and you can see the difference between how much more porous this sample is compared to the sample on the left. So the sample on the right is the one from residual soils. The sample on the left is from the completely weathered rock. So this is now the same sample as in the video, just with the slice and then also the porosity analysis enabled. So the color scale is still there, showing the pores, and then you can still see the structure and the density of the slice. So what I wanted to show you is that the structure on the top view is running kind of here between those two yellow brackets, and then on the side view, kind of runs there. And the denser material, which will be your brighter material, your more white material, kind of solely occurs in these structures. So there's another structure running here, left to right. So and what that tells us is that from looking at the logs, looking at the CT scan, and looking at kind of stereo microscopes, is that the relic rock structures have infill, and that infill has been coated and the joint stained by iron and manganese oxides, which is very dense, much more dense than the surrounding kaolinite. That's what stands out like it does on the CT scans. So hematite is a very typical iron oxide that happens in ferrocretes and nodules and staining as a 5.2 density, and then kaolinite is 2.6. And what we use for this is that we can determine where the flow happens, because it's very tough to do kind of a triaxial and then see where the flow is happening. So using pedology, theories from pedology, we're kind of trying to figure out where that boundary happens, where the flow will happen as kind of a homogeneous flow through the primary pores, or does it still follow the secondary structures from the relic rock structure? Other data you can pull out from the CT scan is sphericity versus effective diameter of each pore. So here are the three samples we looked at, and what you can see is one is the most spherical, so it's essentially a perfect ball, and then 0 is not a perfect ball at all. And you can see as the effective diameter of the pores increase, the sphericity becomes less. So the smaller the pore, the more it tends closer to a ball shape. The bigger the pore, the more stressed out it is, which makes sense if you remember the video. Everything is orientated and the pores are quite long, and the secondary fractures, which are based on the relic rock structure. So if we take that data and other data that other tests we did that I can't cover here, and put it back into the weathering profile. So you have your sample locations, you have this increase in the state of weathering. you will then have these different structural profiles, vertical structural profiles. If you follow with me, generally bulk density starts at a certain point and decreases, carries on decreasing through the residual, but at some point in the residual, it will be too voided and it will collapse on itself, whereby compacting, and you get an increase in bulk density. And just for interest sake, that's typically where your ferrocretes form, because that's as the water comes through the topsoil or the transported soil, it'll hit that densified layer, and then it will go lateral. It will flow laterally, and that kind of is where your ferrocretes like to form, with that sitting water. And yeah, the void ratio, or the water storage here, the green one, will just be inversely proportional to the bulk density, and then your void ratio generally increases all the way up. For your primary process and secondary process is based on your relic rock structure. So that will be the most open in a competent rock, and then as weathering occurs, the joints will fill up, will have infill, and then also the faces will get weathered and then also fall in to the joint. So then if you continue that into completely weathered rock, your secondary process generally decreases to a point where your rock structure is lost due to this compaction or this collapse of the residual, and then you essentially have no more secondary porosity, and your primary porosity will generally increase with a decrease on the compaction. So that was looking at the structure of the Dullstroom lavas. I'm now shifting over to dolomite residuum. This is just to give you context of where the sample sites are. I did across where I could get samples. I was looking for WOD on the manganese-rich dolomites, the Chertpuer dolomites. So just for definition purposes, what do we call it? Meaning, there are different types of residual soils from dolomite. We get Verona soils, which is your red iron-rich soils. They can be structured, non-structured. You get your manganiferous soils, which is your WOD. It's black to purple and very low density manganese-rich, and that can also be non-structured or structured. And then you get an idea of reworked residuum, where one of these two types of soils rework to the point where it loses either the structure, or for WOD's sake, loses the structure and then also the manganese-rich components. And just to highlight that the definition of dolomite residuum is based on chemistry and secondarily on structure. How does it form? It forms the same way as the previous weathering profile I explained to you. You get your rock at surface, it rains, the water moves down. But what's interesting about this one is that all your main constituents of the rock will leach away, which is typical of karst. That's how your caves and things form. But then you're also left with if the thing doesn't collapse and the rock volume remains the same, then your trace elements would then occupy that space. So that's kind of how your WOD forms. It's the trace elements in the dolomite, which is usually less than 3% manganese, then occupies that entire space with some iron and some silica, and then you get this very, very low density material. But what is it made of? WOD? It's mainly manganese oxides, but there's different types. There's different types of manganese oxides. The most common one, which you kind of see at the high felt, is bernicite, or kind of south of Pretoria is bernicite. It's grades as a silt, and it can swap out with that's what I say, iron. It can swap out with iron quite readily. The second most common one is this lithiophoreite. It's a clay soil. This occurs more in the eastern escarpment by Graskop and Sabi in those areas. And then you get these two, which aren't as common, but this manganite forms in your ferrocrete, the Mn nodules and concretions that you get. This is a SEM scan of a WOD sample. And what you're seeing on the left is kind of a bit more zoomed out, but this across is 80 microns. This is a silica grain, could have formed from various stuff, but you generally get these bigger silica grains in this matrix of finer manganese and iron particles. If you zoom in on one of those, this is bernocite. It's typically that has a coral to sponge type structure, and its surface area, it's very, very high. It's 300 meters squared per gram. So that's your smectites are kind of sitting at 600. So you're very close to that. There's not many minerals that have such a high surface area, and because it has such a high surface area, it can take up a lot of water. You can see that it looks like a sponge or coral, and that can suck up water quite a lot. This is just more photos of the bernocite. So one of my questions, well, when I was doing this, because I was trying to find the WOD, I couldn't figure out, why is there WOD here and not there? And the only study that I could find was done by soil scientists who looked at the manganese toxicity in pine trees along the eastern escarpment. And what they found was that if the soil stays moist, the manganese in the bernocite crystal doesn't mobilize. It stays in there, and the mineral remains bernocite. But if it dries out through a fault fire or a drought period, the trees then tend to be poisoned or have toxicity from abundant manganese in the soil, and that's because the manganese then, when the soil dries out, the manganese is released from the crystal structure, which is then taken up by plants. Same mechanism. If there wasn't a plant, it would just flow away with water passing through. So just to kind of show this in diagram, you have bernocite on the left. It's a sponge. If it stays moist, it stays a sponge. But if it dries out, the manganese will move out of the crystal ladders. Usually it's replaced by iron, and then your manganese somewhere else in the profile will gather and become nodules. And you can imagine these two materials have similar manganese contents, but they're going to have very different behaviors in water storage and unsaturated behavior. So just show it in the profiles. This is Graskop. If you dig there, you find WOD. It's very easy to find WOD there. It's generally wet. The above profile, I can't see it in this photo, but this is abundant nodules and stuff in here from higher up the slope where the manganese has mobilized. And then if you look at it from a stereo microscope, it's generally fine. It's somewhat a salt with good distribution of color and grain size. And then this is in the high fault. So even in Pretoria, where it's a bit drier, this site had a stream passing through it. So the WOD could stay wet, so it remained in profile. And then your bernocite will then remain, which will then give its high water content abilities to the soil. Whereas in dry areas, and this is now most of South Africa, the soil tends to go red. It's because when it dries out, the manganese swaps up with the iron, it turns the soil red. And then on the right here, you can see the manganese nodules have formed, and the silica that remains is kind of stained red, and so as the kind of finer material. And over time, from a macro scale, the soil will be red, even though it will still have 30% manganese, but it won't have the behavior of bernocite or what those manganese oxides give you. So the point I'm trying to get across is that the manganese oxides contributes to the water holding capacity, and it gives the water ability to have very high liquid limits. So this is just a diagram from Wesley, which I added the WOD in, just to kind of show there are other soils that can have very high liquid limits. And reworking essentially reduces the water storage ability. So it's also an indicator of how reworked the material is. And this also can kind of, we haven't tested it yet, but it also opens the eyes to how does reworking affect the stability of a sinkhole. If the stuff stays moist, it'll have, actually I'll leave that to the soil water retention curve. But yeah, this is what the Mn oxides do. So now we look at the structure of the WOD. So what is structured or non-structured? There are two examples of that. This exact sample, this is its parameters here on the left. So it's mainly a silt, has extremely high liquid limits, generally low PI. Its manganese oxide content is 45. The rest of it was, I think, iron and silica. And then your void ratio is extremely high, 8.32. That's a mixture. That's due to the structure, macrostructure that's present, because it's a extremely low dense material from the weathering process, and then also the burner-side mineral in it. And density was quite low, and that saturation had a moisture content of 300%. We did saltwater retention curves on it at Tux. The curve on the left is for the structured WAD. The measured are the X's, which have kind of, because that tensiometer is so good, it kind of measured so even it's a line. So it's kind of the X's have joined to make a line, and then we use the Fredholm and Zing equation to kind of extrapolate that curve. And then we took that material in that test ring, and we remolded it, try to get it back to the same density, but getting it to 300 kilograms per meter cubed is a bit tough. But we also tested it and got the cube and got the curve and the extrapolate with the equations. So these are those structured remolded sample on the same graph, the volumetric water content on the left. And these are just to compare the two samples. So density was as close as possible I could get it. So it's 450 and 300. I know the curve would change with the change in density, but when the material is remolded or reworked in nature, it would densify. It wouldn't go become lighter than what it is in situ. So I guess it's somewhat true. So but breaking down of the relic structure, you had different moisture content, saturation, the remold at 87, whereas the structure had 300. Void ratio has also changed. The remold still had a very high void ratio of 2. And the changes in the curves will be due to the changes in pore sizes, shape, and distribution. And then I just want to highlight the point I was talking about the sinkholes, is that if you had a material at a certain suction, let's say 100, and you've wet it or dry it, then there isn't much change in the suctions over a wide range of moisture content, where for the remolder without its structure in place, the same change will result in a much bigger suction change behavior. So that just tells me that influencing or impacting the structure of WAD, which usually sits at the throat of where sinkhole forms, could be a very important thing that we need to consider when modeling this in future. Just something to think about. So if we just put this all together in a weathering profile again, this is now for the dolomites. Here you have a chemistry profile. So your WAD, which is kind of like a completely weathered dolomite. I don't want to use weathered altered dolomite, but you'll have a lot of manganese oxides, and then as the weathering and reworking occurs, you generally have a decrease in manganese oxides, and you have still a very high iron oxide amount in the WAD, but that kind of slightly increases as the weathering increases. And then you have various other minerals that kind of increase as you go up. This is now testing that I didn't show today, but it's there. And then the structure profiles also, as you have bulk density starts high, in a very short time becomes extremely low for the WAD, and then the WAD either densifies or the manganese and iron gets swapped out, which increases the density. Void ratio is opposite to that. Water storage also decreases, increase in reworking, and then the permeability generally improves with low manganese contents, and then also the structure breaking down. Yeah, so that's kind of the presentation. I don't know why I'm concluding here. I guess I just told you guys a story and showed you some photos, but this was all done on completely weathered rock, which would test as extremely weak rock, so less than 1 MPa. So a lot of people will treat it as a soil. That's kind of the line for engineers. But generally the in situ properties are governed by the structure, and mainly by the structure, but then sometimes you get a unique mineral material like WAD that has a big influence on its chemistry, And then, this will depend. This is not for all weathered material. It depends on the rock type. water flow regime, where it is on the slope. If it's waterlogged, smectites will form. If it's high up, it will be kind of your kaolinites. So dependent on a bunch of stuff. And then just to highlight that the completely weathered and residual zones are generally metastable. As soon as you expose it to the Earth's surface, it's in a state that it's never been before, and it would generally rapidly weather and usually decreasing in or have worse parameters over time. So it will never get better. It'll always become worse in terms of a geotechnical point of view. Yeah, that's the presentation. I hope I caught us up a bit. Thank you to the funders. Yeah, I'll take any questions. Thanks.
Thank you, Duan. You definitely made up some time there. We've got a couple of minutes for some questions, either for Ruan or Duan. If you've got a question, just pop it in the Q&A section, or I believe you can also just put your question in the comments section. We'll give about a minute to see if there's any questions.
I was saying, perhaps while we wait, I've actually got a question for Duan. We chatted very briefly after YGE about CT scanning, and I've forgotten what your answer actually was. But with that X-ray CT scanning, what is the minimum size of a pore that you're able to detect using that technique?
So it depends on the CT scan machine, I think, but we have quite a good team sitting just outside outside Stellenbosch called X-Site. They can go low, or they tell me they can go as low as 0.2 of a nanometer. They can have a pixel on their CT scan, which then the pixel can then either be occupied by air, which is a void, or material. So it depends on your sample size as well. So you generally have to kind of send in a 5 centimeter by 5 centimeter sample cube to get to that sort of how do you say, detail in the scans. So I'm sure that'll be fine for you, because you're dealing with generally homogeneous material, or at least units. So yeah, you could probably get to that extent.
Yeah, no, that would definitely be useful for my work. So that's something I'll look into. Thank you.
Thanks for that, Ruan. Okay, it doesn't seem like there's any questions or comments from the floor. I believe you're welcome to contact either of the presenters if you have any further questions or comments. I'm sure they'd be glad or happy to assist you. That brings tonight's evening lecture to an end. Thank you again to the presenters for making yourselves available to share this information with a wider geotechnical fraternity, and congratulations again. Excellent papers and presentations. We still have a couple more evening lectures planned for 2024, so please keep an eye out for the dates and times and the GeoDiv announcement and newsletters. Till next time, good night.